Okay, pre-calc. Today we're going to be talking about rational functions in more depth. So I'm going to do a little bit of reading. Bear with me when we get to the problems. I think this will make a lot more sense. So, okay, now you know about rate as an organizational method for analyzing rational functions. There are a few more techniques you need to know about. How do you find the domain of a rational function? How can you tell quickly if you have a horizontal or slant asymptote? How do you find end behavior when the denominator or numerator don't factor? How can you tell if a function crosses an end behavior asymptote? What happens when a common factor in the numerator and denominator cancel? So let's see here. So the domain, this is the set of all real numbers that are not a zero of the denominator. Before the function has been simplified, common factors cancel if possible. Remember, zeros of the denominator where the function is undefined are vertical asymptotes of the function after it's been simplified. So what this is essentially saying is when you're looking at it, when you graph the function, if you have a vertical asymptote or a hole, those would be places that you would not have a function, and those typically occur with respect to issues with the denominator. Okay, so again, when I do an actual example, I think it'll make more sense. But let's go on to the next one. How to quickly recognize the type of asymptote. Okay, so determine the characteristics of a polynomial in both the numerator and denominator. The numerator has a leading coefficient of a, degree n, and constant term c. The denominator has a leading coefficient b, degree m, and constant term d, such that. Okay, so basically this is the setup to which they're using to describe what's occurring right here. If n is less than m, so I'm going to use the term bottom heavy. This is the scenario where the denominator is bigger than the numerator. I'll go plus one for both of these. Okay, so when you have two polynomials and the denominator is bigger than the numerator, you end up getting a horizontal asymptote of y equals 0. What you can do, you don't have to memorize this. You just think about it for a second, right? If you have x cubed in the denominator and x in the numerator, which one's growing faster, the numerator or the denominator? Well, clearly the denominator would be the one that's growing faster. So what I'm saying is, over time, you're going to have the effect of going 1 over 2, 1 over 3, 1 over 4, 1 over 5. Maybe not exactly this, but what's going to happen over time is you're going to have a denominator that grows more and more and more, which means the number is going to get closer and closer to what? Well, if you think about it, if we use the example of 1/2, 1/3, 1/4, 1/5, you're going 0.5, 0.33, 0.25, 0.20, so on and so forth. You're gradually approaching 0, and that's why the horizontal asymptote is y equals 0. If they're equal, then you divide the coefficients, and this is we've already talked about. This is the situation if you have something like 3x to the fourth plus, let's say, 2x over 5x to the fourth plus 7, right? So again, we're only concerned with the leading coefficients. They're the same, so you're doing 3 times a big number to the fourth over 5 times a big number to the fourth, right? What's going to happen? These are going to divide out, and you're going to just be left with 3 over 5, which are the leading coefficients. And that's what the second one is saying. Okay. Then it says if n is greater than m, then you do not have a horizontal asymptote. And that should make sense as well. We haven't talked about that yet. But if you have an x cubed, let's say plus 6, the bottom is x squared minus 2x. This function is going to be, we know that this is not going to be horizontal. Why do we know this is going to be horizontal? Because if the numerator is growing faster than the denominator, this thing is going to head towards infinity, right? So it's not that you're not going to have a 0. You're actually going to end up having what's called a slant. Now, the slant is the byproduct of the fact that when you divide them, you create a linear function. And I'll talk more about that a little bit later. You don't actually have to just have a slant. It could be the asymptote can actually become cubic. It could be quadratic. It could be a lot of different things. But what you'll typically see is just this difference of 1. Hence, you see my example of saying x cubed over x squared, where the difference between these is 1. That's what you're typically going to see for us, just for simplistic reasons. Okay, we'll do an example later on about this. Okay, what does it say? This is a line, so you need a slope and a y-intercept. You need to do long division in order to determine the quotient. The quotient will be a line. The remainder will be 0 as you consider values of x that go towards infinity. Don't stress too much about that. When we do an example, you'll understand why. Okay, to determine if a rational function crosses its end behavior, determine the end behavior, set the rational function equal to the end behavior, and solve. So, if you can solve the equation for the horizontal asymptote, then it crosses the horizontal asymptote. Seems common sense. When a factor is and this is the part that's actually really important. When a factor and the numerator and denominator cancel. So what we're saying is, if you have something like the effect of x plus 1, x plus 2 over x plus 1, because x plus 1s match up, these will divide out, and what you'll end up getting is a whole. So whatever this function will actually become is exactly like y equals x plus 2, which we know what that is. That looks something like this, crossing at 2, slope of 1. And the only difference here is that it does not exist. The only difference between the equation y equals x plus 2 and our rational function is that at -2, we have a whole. It does not exist at -2. Now, I don't know exactly where -2 is. I'm just putting a random point there. But wherever -2 is, there's going to be a whole. And so it says, after you canceling, determine what type of end behavior and asymptote you have in the previous method. When you sketch the graph, don't forget to include the whole. So what this is a long-winded way of saying is, you cancel it out, draw the graph of what you have left, and whatever gets canceled out, there's going to be a whole. Now, I made a mistake. I said -2. I apologize. This is actually -1 because that's what we canceled out. Sorry, I glanced at it wrong. Okay, so it's at -1. So if you were confused earlier, I apologize. Okay, so here we have an example of what's going on. So the first thing we want to do, well, first thing I'm going to do is rewrite it. And the next thing I'm going to do is I'm going to factor this out as much as I can. So I know the numerator is going to factor to x minus 4 times x plus 1. The denominator I'm going to factor out at 2x. And so now we're going to look at this, and we're going to make a couple of decisions here. So looking at this, we have to see, does anything divide out? And clearly we're not seeing anything dividing out. So let's see what we can do here. So the first part here says this is, well, you know what? I'm just going to use, let's just do this. So let's just solve that real fast. So what are the roots? The roots are when the denominator is equal to 0, and if I need to do this in more depth, let me know and I will. It's going to be x is 4 and x is equal to -1, because 4 minus 4 is 0 and -1 plus 1 is 0. Boom. Then we have a, and so this is about the asymptotes. Now, full disclosure here, you could have a question where the asymptotes cancel out, where you have the numerator and denominator cancel out. And in that case, it's not an asymptote, that's a whole. So I want to make sure you're looking out for that. Here we don't have anything canceling out, so we're going to say, looks like we're going to have asymptote at x equals 0 and x equals -2. So we have vertical asymptotes at 0 and -2. Then we have t, which is togetherness, and so that has to deal with the fact if the numerator and denominator have even roots, or the denominators has an even factor in there. That's not going on, so this is, I'm just going to go with NA, not applicable. Okay, what's the next one? I don't know. This is not what I usually do. Exponent. Okay, so the exponent deals with, I just said exponent, end behavior, sorry. So let's look at the end behavior. So what we want to do really, actually what you really want is you want to consider, oops, let me do that again. You want to consider the original format of it, right? And we can see since this top and the bottom match up, this is 1/2. So this function, end behavior is really saying what's the horizontal asymptote. And we can say the horizontal asymptote is y equals 1/2. Because there's a 1 here and there's a 2 here. And so when you divide, because the exponents are the same, you get 1/2. And please let me know if there needs to be more depth in terms of the explanation. Last time I went in a lot of depth. This time I'm not going to do so much. Last one is y. So y is the Y-intercept, and what do we know about the Y-intercept? The Y-intercept is when x equals 0. So let's see what that becomes. So the function is, I'm going to rewrite the function. It's f of x equals x squared minus 3x minus 4 over 2x squared plus 4x. So you can see here that if x is 0, right, then what's going to happen? Well, everything's going to go away except for the -4, and then we're going to have 0 on the bottom. But you can't have 0 on the bottom because that's undefined. So what this is telling me is that there is no Y-intercept. Now, here's something else we want to see here. Does that make sense to not have Y-intercept? Well, it really does, and I really shouldn't have even had to do this because right here, x equals 0 means it's crossing the Y. We have a vertical asymptote at the Y-intercept. Okay, and with all of this done, we can begin to draw the graph. And so let's just put it here. So we know we have at 4 and at -1. So here's 4, here's -1. Oh, I'm so sorry. I did that wrong. I was still thinking about asymptotes. I hope you were looking at this video like, what does this crazy man do it? Right? This is 4, so where it crosses here. And here's at -1. We know we have the asymptote. Now we know we have an asymptote there. You know what? Let's do a different color. Let's do purple. That sticks out more. At 0, and then we also have one at -2. Okay, and when we know we have a horizontal asymptote at y equals 1/2. Okay, and yeah, and that's pretty much it because we don't have a Y-intercept. Let's go back here and see. To determine if the rational function crosses its end behavior, it says set the function equal to the end behavior. So we're going to do that. Let's see if I can remember this. 1/2 is going to equal to the function, and I'm going to do the factored form. Actually, you know what? Let's not do the factored form. We don't need it. We don't need that. Let's do x squared minus 3x minus 4 over 2x squared plus 4x. Okay, so notice I'm going from here because that's our original function, and then we just solve it. So get rid of the fraction, multiply both sides by 2x squared plus 4x, and you can quickly see, oh look, the problem is cooked up. And so when I solve this, we end up getting x squared plus 2x equals x squared minus 3x minus 4. And then we just keep solving. So it's nice, the x squareds will divide out. I'm going to subtract 2x from both sides. Actually, let me not subtract 2x. I'm actually going to add 3x. And that makes sense, right, to add 3x to both sides, because then we put our x's together. And then I'm going to divide through by 5. X, ran out of space. X equals negative 4/5. So what that means is at x equals negative 4/5, at x equals negative 4/5, which would be right here. So let's say it's going to cross the asymptote. So we know it's crossing the asymptote. Okay, so we have an idea what the picture looks like. One of the things I had suggested is if you are not 100% certain, then you can always pick values, some additional values to confirm what's going on, right? So maybe I want to pick something after. I should have probably labeled this as -2 at this asymptote of -2. So maybe I want to plug in -3. Let's say I plug -3 here, 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 and here. Let's see what happens. So that gives me -7. This will become -7 times -2 over -6 times -1. And that's going to be 14 over 6. Okay. So 14 over 6 is 2 and some change. And so we know that this is going to be living somewhere here, so we can assume that we have this effect going on here. Maybe I want to pick another. Well, I know that this has to be going like this. So it's probably doing this. Actually, it has to do this because if the asymptote is here, and we're only crossing here, then that's the only place. This part here has to be going down, right? And then on the other one, we know that it has to be going like this. Keep in mind that we know already that our roots, they're crossing through the roots. So our picture looks something like that. So let's look at this next one. F of x equals x plus 2 over x plus 2. This one's actually a lot easier. So let's first off, let's write this out. Okay, the first thing I want you to see, and I'm laughing, and hopefully you see why I'm laughing, is that if x plus 2 is over x plus 2, this thing divides out to becoming 1. So this is the f of x equals 1. So that's actually what I'm playing with, except because of the whole. So whatever cancels out, you have a whole, except for the whole. So whatever something cancels out, it's a whole. The whole is at x equals -2. Because you can't do 0 divided by 0. So the whole is existing at -2. So if you... Well, this is an interesting case, because if it's y equals 1, then we know it's going to look like this. And then we know we have a whole at -2. So we don't have to even really figure out when x is negative. I don't want to do that. I'm sorry. I'm making it look like an asymptote. But this is at -2. Okay. So at -2, 1, and you know it's got to be -2, 1 because it's a straight line. You have a whole. So are there roots? None. Asymptotes? None. This is not necessary. No. This thing is just one line. It's always extending out. So the end behavior is just going to be. I guess you could say the end behavior is y equals 1 because it goes out to 1. And then the Y-intercept is at 1. So if you wanted to, you could do that. This is pretty straightforward. Next one. All right. Here we see the same thing. So I'm just going to go ahead and start this off by saying, hey, those are going to divide out. We're going to be left with x plus 2. So this is just y equals x plus 2. So what does this mean? This means if I'm to draw this out, I really can just go right at it. It's going to look like this. It's crossing at plus 2. There's a hole at x equals 3, though, right? Because if you plug 3 in here, 3 minus 3 is 0. So that's the only thing. You have a hole at 0. Now, here's a little more interesting, because now we have to figure out what the y component is. The last one, all the y values are the same. This thing's at 1, right? It's crossing the y-axis at 1. So we know that one. That was pretty straightforward. Here, what you do is you take the 0 and you plug it back in, and you're going to get 0 plus 2, which is 2. So this means that this thing crosses at, I'm sorry, I read that wrong. It's crossing at 3. So we have 3 plus 2, which is 5. There we go, 5. Sorry about that. So we know now that it crosses at 3, 5. Let's say that it's right there. There's 3 comma 5. That's where it's crossing at. Okay? And so that's where we have a hole. Okay? Dramatic purposes, I drew that really big. Okay? So that's basically it. Now, if we want to figure out the root, right, we can still play this game, right? What's going to be, let's write it out. Let's write it out. Okay? So what are my roots? The root is when is the x-intercept, so that's when y is 0, so 0 equals x plus 2. So that is when x equals negative 2. So we know it's crossing here at negative 2. We know it has no asymptotes. We don't have to worry about this togetherness. No. We know this is just a diagonal line, so this is I'm just going to say no. What's the y-intercept? Well, it's x plus 2. It's dead 2. So this is 0, comma 2. So this is why I'm more of a fan of understanding what's going on, because if you understand what's going on, you just kind of just get the graph done just by thinking about it naturally. But whatever works, let's go on to the next one. So once again, we know that this divides out, and so we're left with 1 over x minus 5. We know that 1 over x minus 5, hopefully we remember this from algebra 2, this is a rational function. So quick sketch, a rational function. The parent function looks like so. And so what do we know about this? We're going to shift this over to 5. So in our picture, we have an asymptote at 5. And then we're going to draw the graph. So I know that, like, if I was to quick sketch it, because of what this is, I also know that this is going through here like so. I know it's going to look something like this. And like this, because that's what the function looks like. But we do want to be more precise here. So we want to figure out the y-intercept, for example, and some of these other things. So let's write out rate. Okay. So the roots. Well, we know we're not. So like, okay, sorry. I just have to immediately go to the end behavior and just say, like, we know this is y equals 0. So what I'm hoping is that in your mind you should have this function memorized from previous class. So you should know that's what it looks like. You can use the rules to which we've spoken of, which are that if it's bottom heavy, right? Bottom heavy means it's just going to be y equals 0. So that's how I know that's going to be the case. But really, you should know from the parent function. We also know that the asymptote is x equals 5, because if you plug 5 into the denominator, you get an asymptote. So this is at 5. Hence the shifting. We don't have to worry about togetherness. No. And the roots, because you have an asymptote at 0, so it's not going to cross. you technically could say, hey, does 0 equals 1 over x minus 5? Because it could technically cross the asymptote. Just because you have an asymptote doesn't mean it doesn't cross it. But if you multiply both sides by x minus 5, you get stuff that makes no sense. You get 1 equals 0, and that makes no sense. So I'm not going to worry about that. So this is no, none, whatever you want to call it. And then we're going to go to the Y-intercept. This is the one time that it does exist. This is one thing that does exist. So Y-intercept is when x equals 0. So this is going to be, I'll write it out. So if I have y equals 1 over x minus 5, and Y-intercept is when x equals 0, right? We get y equals negative 1/5, and hence this is going to be 0, negative 1/5. And we can look at this picture and we can say, yeah, it kind of makes sense, right? Right? Negative 1/5 makes sense. 0, negative 1/5. Last bit, we want to put the whole, right? So remember that when we originally looked at this question right here, x equals negative 2. So at negative 2 we have a whole. So I'm going to take y equals 1 over x minus 5. I'm going to plug in negative 2. And I'm going to get y equals negative 1 over 7. So we know at negative 2, it's crossing at negative 1/7. And so there we have it. All right, one more. So here we're going to factor. If we can. I don't know why I was rewriting it. I was rewriting it because I don't think we can factor it. Let's see here. We can do... if it's going to work, it's got to be minus 3 plus 2, right? Because that'll give me negative 1 in the middle and negative 6 back. Yeah, it does work. Look at that. Okay. Now, I got to be kind of fast here because I only got about 2.5 minutes. So this one, you know what? I'm actually going to stop here. I want you guys to go ahead and try this one on your own, and then next time I will show you guys how to do this. It's going to be a little bit harder to do this, take more than about 2 minutes to do this. So I'm going to stop right here. Y'all try this one on your own, and we'll talk about it next time.